some of you at least saw. And I am sorry that the crowd is a bit small. We have some faculty members. I hope that some students will still come for the lectures because the greetings are not important, right? So that they hopefully will still show up. And what is very unfortunate from my point of view is that we have very few of the Board of Governors members, but we have kind of a very concentrated schedule of a week of various activities and sometimes parallel to one another and so on, and therefore, and I will have to be running soon to something else. We have this morning the discussion summarizing the board meeting, which will begin in about an hour. So I will not stay long here. But it gives me really great pleasure. I was not even sure that I would be able to come this time, and as you can see, my name is not there. Of course, what I wanted to say when I saw it first, well, I don't need introduction. I don't need to have my name there. Everybody knows me. But that's, of course, not the case. Even not at this university, I guess. But, and of course, spelling my name is something terrible today. In today's newspaper, my name is spelled wrong when the newspaper gave some words about yesterday's meeting. But anyway, it really is an important, very important subject these days, the question of the environment and learning, well, hoping to learn how to cope and hoping to learn from the past, maybe, I should add maybe, but you also said maybe, what we can expect and how to deal with it maybe is very important because, when it started with global warming and so on, I said to myself, and I'm a mathematician, so I'm very far from science, I guess, although it's the mother of sciences. And I said to myself, well, I don't feel it's getting so warm in Israel. It's always warm. But it seems that global warming means in general unstable weather of all kinds. And what we see in recent years with storms and so on definitely is part of this problem. And as Al Gore said yesterday, we are at the last moment before catastrophe will happen. And I mean catastrophe not by mean of a tsunami or the cyclone or the tornadoes in the United States recently, or, well, earthquakes happened all throughout, I guess, so I will not mention China. But something that we will not be able to recover from in general. So I do hope that you will find ways to help us on that. And I wish you a good day of deliberations or half day of deliberations. And I let the Dean say a few words.
The Dean, thank you. Thank you, Danny Leviatan, our Dean of Faculty of Exact Sciences, Professor Chaim Wolfson.
Thank you, Pinchas. So, although I am the Dean of the Faculty of Exact Sciences and Geosciences is one of the areas that belong to our faculty, I by myself am a computer scientist, and I must admit that I am not well aware of the work that was done. So naturally, for a computer scientist, I just Googled the names of our prize laureates and printed the first few citations on each of them. And I'm going to read everything that is here to you. So, first of all, I realized that this is not the first prize that our laureates are receiving. And I randomly picked citations from several prizes, and I'll start with Professor Eglinton. In the citation to the 1999 Martin Gold Medal, opens with a sentence, Jeff Eglinton is one of the founding fathers of modern organic geochemistry and is responsible for many of the geochemical tools and concepts that earth sciences today take for granted. A year later, at the citation for the 2000 Goldschmidt Award, the speaker said, he will probably blame someone else for founding the field of organic geochemistry. Nevertheless, most prominent organic geochemists recognize him as a pioneer of molecular organic geochemistry and modern biogeochemistry. Well, we know that fatherhood issues are sticky things, but still, it seems that here there is a consensus. And I also looked at the personal webpage of Professor Eglinton, where one of the second sentence, I guess, says, currently we are completing a 9-site north-south transect in South Atlantic of Southern Africa. The study relates the distributions and isotopic contents of individual N-alkane and N-alkanol homologs to the contents of different pollen grains in the sediment cores at 4 times horizons over the last 130K years. Well, I guess everything is clear now. But I would like to point out the last few words, 130K years. And I'll soon give citations from Professor Ellen and Lonnie Thompson. And after reading both of these, I realized that actually our prize laureates deserve the Dan David Prize in all 3 dimensions. Yeah, simply the committee wanted to give something to the other people as well. So they didn't distribute all 3 prizes to our distinguished guests here. A citation from an interview with Professor Ellen Thompson, where she says, from a personal point of view, I really promoted high-resolution studies within the I-score community, that is, changes over years, decades, and centuries, rather than millennia, because those are the timescales on which climate changes affect people. Lonnie and I also led the glaciology community from the poles into the tropics. And from the non-scientific side, I'm proud to witness the increase in the number of women in geophysics. I started going to Antarctica in the 1980s and was one of the first women to lead my own field teams here. I like to think I helped open the door to for other women. And from a profile of Professor Lonnie Thompson, which was published in the Proceedings of National Academy of Sciences, what he says, within the bustling campus of Ohio State University rests one of the most extensive archives of the Earth's history, chronicling the past 700,000 years. So first we were impressed by 130K years. Now we're talking about 700,000 years. Visually, this repository may not appear impressive. No fossils or pottery fragments, just ice lots and lots of ice. Over 7,000 meters of glacial ice, to be exact, have been collected from some of the most imposing mountaintops of the world, the Andes, the Himalayas, even the snows of Mount Kilimanjaro. So when I read this, it reminded me some personal story. So let me just waste you another 2 minutes before some of the students arrive and tell you a story, a real personal story. I mean, I was not born in Israel. I was born in an empire, which was once called the Evil Empire, where the climate was cold and the politics were frozen. And my parents were kind enough to bring me here at the age of 15 to sew up. So I vividly remember that I guess it was at the age of 3 or something like that. I went to play. It was winter. I was playing in the snow. And then my grandmother told me we must go home to take the afternoon nap. But I didn't want to part with the snow. I had this small metal candy box, which was the way candies were sold at that time. So I decided to put some snow into the candy box, go home to have the nap and play with the snow later. Well, so that's what I did. And when I woke up, I was really disappointed to discover just a bit of water in the candy box.
This is why you became a computer scientist, not a real scientist.
Yeah. So, well, I must say that it is not that I didn't know that snow does not melt. I really was aware of it. I just thought that, in general, if I want the snow to wait for me after I have this nap, so I'm following all these fairy tales that I was told every evening before sleep, the snow should wait for me. And in a way, hearing all these talks about the global warming and the climate change, I somehow get the feeling that we, as a universe, sort of took the snow in this candy box and went to sleep. And I am glad that our distinguished laureates actually are trying to wake us up before the snow melts. So thank you very much for giving us this opportunity, and I congratulate you with the prize.
Thank you, Chaim. I wish to invite now the Dan David laureates and start with Ellen Mosley and Lonnie Thompson. While you put your presentation, I want to make 2 comments because I am looking very much forward to listen to you. I was using your figures in my lectures, and I never knew really who are the people behind these important, very important figures. I'm an atmospheric dynamicist, climate researcher, and this is being used by many people, but it's nice to see who are these people. I want to make one comment also. Last night we had a wonderful Dan David ceremony, and one of the people there, I don't remember who was it, who said, and I liked it, that the ice cores are the library of the earth. And he called you the librarians. I think this is really a humble thing to say, because you are providing really, or discovering the typewriters, the machines, or the tools that are translating these ice cores into what is useful for the scientist. And I wish you now to invite Ellen Mosley and Lonnie, who is going to start. Okay, so Ellen, please, I will move over there so I can listen to you.
Before I start, let me just ask, can you hear me, or do I need to use this? Maybe I should use it? You can hear me? I mean, it seems like the good acoustics. Okay. Oh, from afar. All right. I have a tendency to talk a little bit fast. I'm supposed to talk about 20 minutes, but if I am talking too quickly, just put up your hand and I will try to slow down. So I like to start with this slide, which is a nighttime image of the planet, because it really shows how heavy the human footprint is on our Earth. The lights that you see are electricity primarily generated from, about half of that is generated from coal-burning power plants. Much of the rest is hydroelectric power and nuclear power. So I want to point out that first, Lonnie and I are very thrilled to be here. It's an honor to have received the Dan David Prize last night and to be with you today. But the work that we're presenting represents the collective efforts of our research group, shown here, and our graduate students. And two of our students, Natalie Kerwald and Li Xiaowei, are receiving the scholarships. They're each getting one of the Dan David scholarships. And then finally, to point out the various agencies that fund our work. So I'm preaching to the crowd here, but we know that the Earth is warming and that our environment is changing. Also, some of the changes that we're observing are occurring on unprecedented timescales. Some on timescales of that are unprecedented for thousands of years. Some of the changes are occurring very rapidly on timescales of years to decades. And some examples that we will show include the shrinking sea ice, the retreating and melting glaciers, but there's a variety of evidence. One that's most evident to everyone is the disruption of ecosystems. The slide here shows what we call our observational record. It extends back about 120 years. It extends back about 160 years. It shows that and this is the globally average temperature of the planet. It shows that there has been an upward trend, indeed, with some variability. 2005 was the warmest year on record. And although this is a global average, and the global average since 1900 has increased about 0.4 of a degree centigrade. But if we look at the global average for, let's just say, the last 7 years, and now we're looking at it spatially, what we see is that the temperatures have not warmed everywhere. We have parts of the planet where we have little change, and areas where the average temperatures have cooled. I want to point out that the largest warming is primarily in the higher latitudes of the northern hemisphere and also in the Antarctic Peninsula. So we know that the climate on our planet has been variable over all time and space scales, and that it's forced by both natural and anthropogenic or human-produced mechanisms. The most prominent natural mechanisms that force climate include changes in the output of the sun, changes in how the radiation received by the top of the atmosphere reaches the Earth's surface. So, for example, changes in the amount of volcanic activity changes the reflectivity of the planet. You might remember back in 1991 when Mount Pinatubo erupted, and the globally average temperatures on the planet ceased to warm for several years. There's also a lot of internal variability in the climate system. So this is the interactions between the ocean and the atmosphere, such as the El Nino Southern Oscillation, the natural variability in the monsoon systems, and for those of us who live around the North Atlantic Oscillation, which is another natural oscillator in the system. But what we also recognize now is that human factors affect climate. Some of the non-natural mechanisms are the increases or the anthropogenic increases in the concentration of atmospheric greenhouse gases, shown here, the increase of carbon dioxide. I'll come back to that. Also changes in aerosol particles, such as those that are released from the burning of fossil fuels, primarily coal. That would be the sulfate aerosols that tend to have a cooling effect. And then the burning of biomass that produces black carbon, that tends to have a warming effect on the radiation balance. And then we're also changing the reflectivity or the albedo of the Earth's surface when we alter the character of the surface. So, for example, changing a forest into an agricultural plot, or, for example, taking a meadow and covering it with asphalt and putting up a shopping mall. It not only changes the radiative properties of the surface, but it also changes the hydrologic properties. So I'm sure you're well aware that last March, 2007, the Intergovernmental Panel on Climate Change, or IPCC, put forth its fourth assessment and made, in the summary for policymakers, they made two important statements. One is that warming of the climate system is unequivocal. So we can move past the discussions of whether the Earth's globally average temperature is warming, to the second statement that most of the observed increase in globally average temperature since mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gases. And I want to point out the asterisk. You're all scientists. You know that scientists never are 100% certain about anything. We always have to speak in with our error bars. And the asterisk means the IPCC was comfortable making this statement with 90% confidence. And those of you, if you're not familiar with the IPCC, this particular assessment was a 3-year assessment. There were 152 authors from 30 countries, over 600 peer reviewers, and the document was approved by 113 governments. The seminal diagram that underpins that second statement is this one from the fourth assessment. And just to walk through the diagram, let's just focus here on the panel for the globally average temperature. And essentially, the Intergovernmental Panel on Climate Change makes its assessments and uses a suite of 17 to 23 climate models to make projections. They have a variety of emissions scenarios. You know, how are we going to power the global economy through, let's say, 2100, through our current century? Well, to make those projections, you have to use a climate model. They have 17 to 23 of them from countries around the world. And of course, if you have a climate model, you have to force it. The dark line here shows the observations. For those in the back, if you can't see it, this is the 20th century. And so the most stringent test that you can give a climate model is asking it to hindcast or predict backward, something that you already know. So here the question was, if these are the observations, and we force the model only with natural forcings, can we get the 20th century temperature trend correctly? And the answer is the models do well up to 1950, but then when the models are forced only by natural forcings, you see that the models cannot capture the increase in temperatures post-1950. And the models can only do this when they are forced with both natural and anthropogenic forcings. And you see this is true for global land, global ocean, and for each of the continents. So these model results gave IPCC the confidence to make that second statement. So the meteorological record is very short. As I mentioned, it only goes back about 160 years. So we have to turn to the archives that provide what we call proxy indicators. They tell us about climate, and there's a variety of these. Dr. Barr Matthews will be talking, and she's an expert in the use of speleothems. but Lonnie and I specialize in the use of ice cores, and Dr. Eglinton specializes in the use of marine records. So the ice caps and ice sheets of the world preserve both long and high-resolution histories. This is the Calcaya ice cap in the southern Andes of Peru. Lonnie will tell you much more about it. Each one of these is an annual layer. So if you drill a core through this ice cap, you literally get a year-by-year proxy history. But if you want, this ice cap provides a record going back several thousand years, which for the modern is, putting the modern in a 2,000-year perspective is very important. In fact, that's the most important part of the history. But if you want a long record, then you have to go to places like Antarctica and Greenland, where the ice sheet is 2 to 3, and in some cases in East Antarctica, 4 kilometers thick. So from these ice sheets, you can get histories that go back hundreds of thousands of years. So I hope to convince you that ice cores are powerful contributors to what we call multi-proxy reconstructions. Those would be reconstructions based upon not just ice cores, but lake cores, ocean cores, corals, tree ring records, as well as, for example, speleothems, stalactites and stalagmites. But coming back to ice cores, they provide multiple lines of evidence of change, both climatic, about changes in climate as well as in the environment. And where we have this high resolution, they're excellent for revealing rapid climate changes. And rapid climate change is something we're very concerned about. This is a shopping list that shows the various types of proxy information that we can extract from ice cores. So we use the oxygen isotopic and the hydrogen isotopic ratio as a proxy for temperature. We can monitor atmospheric chemistry. We can look at periods when the atmosphere was dusty. That might indicate droughts. We can reconstruct volcanic histories and the history of anthropogenic emission. So we go out and we drill these ice cores and we bring them back, but really all we have is a cylinder of ice until we take it and we turn it into what we call an historical record. In other words, we have to take the core that's on a depth scale and we have to convert it to a time scale. And just to give you an example as to how we would go about doing this, for a place like the Calcaya ice cap, you can literally date the core as it comes out of the borehole by looking at these annual dust layers. But most of the polar cores look like this, and you won't see anything that is helpful in terms of dating. So we have to turn to our chemical analysis. This panel shows a section of the core from a place here called D2, where we drilled a core in 1999. This panel shows, this is with depth in meters. This is the seasonal variation in the insoluble dust, the seasonal variations in the oxygen isotopic ratio, and here we have the concentration of what we call beta emitters. That would be, for example, cesium and strontium that emit beta particles as they decay. And these are remnants from thermonuclear testing in the 50s and 60s. And this material was distributed globally. So we can use these, what we call bomb horizons, to identify known stratigraphic units. From that, we can calibrate the upper part of the cores, and then that confirms our seasonal dating. And then deeper in the core, for example, in Greenland and northwest Greenland, you see that the seasonal variations are still well preserved. But in the pre-1950 period, we also have seasonal variations in nitrate. So the more of these seasonally varying parameters that we can analyze, the better job we can do putting a time scale on the ice cores. So just to show you our facilities, this is our Class 100 clean room. where the analyses are made. This is on the back of our building, this is our ice core storage facility. And this is the 2 rooms that store the 7,000 meters of ice core, and they're kept at minus 30 Fahrenheit. Our team also has, we fabricate our own drills. When you hear Lonnie's presentation, you'll see why. Being very light, having our equipment being very light and portable is critical for the high mountain work. So we have a machine shop where our drills are designed by our engineer and fabricated by our machinist. So moving on to the science. So just to give you an example, from an ice core in the central part of Greenland, we can monitor the human pollution of the atmosphere. This is about a 250-year record. And here we're looking at the deposition of sulfate. It's shown in microequivalents per liter. And we see major volcanic eruptions, Laki, Tambora, Cossagina. But around the latter part of the 19th century, we see sulfate deposition peaking around the 20s and 30s, dropping off, and in 1950 taking off. This is the Clean Air Act in the U.S., and it has been dropping. This panel shows nitrate deposition. We know that the nitrogen cycle on the planet is disturbed. Since 1950, we've been adding nitrogen, particularly in the form of fertilizers, and also nitrogen gases, which is a byproduct of the internal combustion engine. In 1950, we produced about 10 million automobiles a year. We now produce between 50 and 55 million automobiles a year. So there's a lot of nitrogen gas being emitted. And a good part of this stays in the northern hemisphere. And if I had shown you an Antarctic graph, it actually would be flat. I thought I might just show you, Lonnie's going to show you all these pretty pictures. The mountains are much nicer to observe than the poor, boring polar ice sheets. But I thought I might show you the most interesting place I've gone. I've been to Antarctica 9 times and Greenland 5 or 6 times. But I went to Seipel Station in 1985. And we go in on the C-130 aircraft. When I got off, I looked around and I said, well, where's the station? Because I had just been working at South Pole Station. Well, the station is 40 feet under the snow. This is a place near the Antarctic Peninsula where we get a lot of accumulation. And so we literally had to climb down this ladder every day, 3 times a day, to go eat in the station under the snow. But Seipel Station is very famous, and you might, everyone in the climate community is aware of what's called the Keeling curve. Charles Keeling started measuring carbon dioxide at Mauna Loa in about 1958. And of course you see what we call the breathing of the planet. That's the up and down that the northern hemisphere growing season sucks CO2 out of the atmosphere. But the trend is what's important, and here you see that it's going up. The primary driver for this is the burning of fossil fuel. But the big question in our community was, what in the world is the earlier record? And after many false starts, it was found that the only way to get that answer is to extract air from bubbles trapped in ice. And those up front might be able to see some of the bubbles in this thin section. So you take the air out of the bubbles. That's not a trivial exercise. There are about 4 or 5 labs in the world that specialize in that. And then you can measure the composition of the various gases. And the Seipel record demonstrated for the first time what the pre-anthropogenic level of CO2 is, 280 parts per million, roughly. Now this record has been extended back. The Vostok ice core extends back over 4 of these glacial interglacial cycles. So it goes back over 400,000 years. In blue, we have the CO2 in parts per million. and in red is methane in parts per billion. So you see that methane and CO2 are higher when the Earth is warmer, and that's lower when the Earth is colder. And this record is important because it puts where we are today in terms of the concentration of these two important gases into nearly a 500,000 year perspective. CO2 is now at 385. And then if we look at where the Intergovernmental Panel on Climate Change projects CO2 might be at the end of our current century, which is only, 92 years away, using a mid-range scenario, A1b, you can see that CO2 could attain a value of 850 parts per million. How we move forward over the next 92 years, what Al Gore talked about last night, is really going to dictate to a large extent where we will be in the future with regard to the concentrations of these gases. The thing to remember about CO2 is that it stays in the atmosphere for 70 to 120 years is the mean residence time. But in 1,000 years, 19% of the CO2 that we are emitting today will still be in the atmosphere. And then Al Gore mentioned last night this new history that was just published a week or so ago in Nature. 2 companion papers showing now the same record I showed you from Vostok. This is from a place called Dome C in East Antarctica, showing the carbon dioxide on red, this is the modern, now going back over 8 glacial, interglacial cycles, and methane, and then the temperature history extracted from the hydrogen isotopic ratio, and again showing in terms of CO2 where we are today. So we're well outside the range of natural variability that has any relevance to humans. And then this is a panel just showing the last 2,000 years. So essentially the rise in these greenhouse gases we could think of as a rapid forcing. It's very rapid, virtually on the time scale of a century or a century and a half. So let's look at how the Earth is responding. I had pointed out that in the Antarctic Peninsula, it's one of the regions where temperatures are warming most strongly. Temperatures have warmed 2.5 degrees C in the last 50 years. And in 1978, John Mercer published a paper in Nature suggesting that one of the first pieces of evidence we might see from anthropogenic warming would be the breakup of the ice shelves along the Antarctic Peninsula. And indeed, in 2002, part of the Larsen B ice shelf broke out in just 31 days, and that made news around the world. Now, the important thing to remember is that these ice shelves don't contribute to sea level because of the differential density between ice and water. But they do buttress or they hold back land-based ice or outlet glaciers. So, for example, these glaciers are now flowing 3 to 8 times faster than they were before 2002. And some of these glaciers have essentially down-wasted or thinned by up to 40 meters in just over a 6-month period following the breakout. On the other hand, these glaciers that are still buttressed by the remaining part of the ice shelf, have not accelerated in terms of flow. But the point is that if you take land-based ice and you put it in the ocean, sea level will rise. So the loss of ice shelves has implications for that. Now, we've drilled cores around Antarctica, and just to give you a synopsis. So in the Antarctic Peninsula, I mentioned that we had this marked warming, and the oxygen isotopic average for the 20th century is shown here, but the warming has been greatest in the last 60 years in the peninsula. On the other hand, we've drilled cores from Cycle Station and over here at Plateau Remote, and those actually show a slight cooling to very little change. So often you will hear about what is called this temperature dipole in the Antarctic. And in fact, you will hear in the contrarian literature the fact that Antarctica is not warming. And in fact, the bulk of the Antarctic ice sheet right now is not warming. The peninsula is warming rapidly. And the reason for this is well understood and has to do in large measure with stratospheric ozone depletion that essentially has strengthened the stratospheric vortex over the Antarctic. And essentially what that does is it isolates the central part of the continent from the more northern latitudes, which essentially is the heat source. And Lonnie and I are fortunate enough that we're going to be part of an International Polar Year project, and we're going to have the opportunity to go in on the icebreaker here into the Larsen B embayment shown here. This is where all that ice broke out. And let me just mention that marine cores from the Larsen B embayment show that this ice had been intact for over 10,000 years. So never in the Holocene had the ice in the Larsen B broken out. So that was, again, an example of a change that is very unusual. And we'll be going in using, and this is not showing up too well, but we'll be using helicopters to come in here to this site, and this on the Bruce Plateau. And this shows you here the Bruce Plateau with the Larsen Ice Shelf in the front. Well, everyone here is aware of what's been happening in the Arctic. Since the beginning of the satellite era in 1979, we've been monitoring the sea ice in the Arctic. This is the extent of the September sea ice. It's always measured at the end of the melt season. And the red line here shows the average for the entire observational period. But in September last year, it reached a new minimum. And the difference here from the average to the new minimum is the area, equals the area of Texas and California. So essentially what has happened is a large part of real estate here, this is a large area, has gone from being highly reflective to being highly absorptive in terms of incoming solar radiation. And in fact, the scientists who study the Arctic sea ice think that it is preconditioned from last year's large loss to set another minimum this year. And we will not know, of course, until September. And then looking at how the Arctic sea ice has diminished at the end of the melt season, the decline was about 9% per decade. And then here's 2007. You can see it seems to have literally fallen off a cliff. And the question that is going around in our community is whether or not we've actually passed a tipping point. And it may be such that the Arctic sea ice may not be able to recover. And that we may have we may be ice-free in the summer as soon as 20 to 30 years, or at least by 2050. Now, just to give you an example of an ice core record from the high Arctic, from the Franz Josef Land. And in Franz Josef Land, it's an archipelago from the Windy Dome ice cap. Our team drilled a 315-meter core there. And this is the oxygen isotopic ratio, again, shown as z-scores. You can see how much warmer the 20th century is relative to the prior 700 years. So this warming in the Arctic is it's very strong and it's relatively recent. We've also drilled ice cores around Greenland as part of PARCA, this Program for Arctic Regional Climate Assessment. And just over 4 years, we added 77 new ice cores around Greenland. And we did this using our lightweight shelters. You can see, for example, might be almost typical working conditions in Greenland, but because of our shelters, we don't lose any time due to weather. And because of our lightweight drills and generators, we can move our camp around the ice sheet in a twin otter. And then, just to show you, for example, the multi-century cores from Greenland, and they all show 20th century warming at different degrees. The greatest warming is right here in west central Greenland. And you may have heard of the Jakobshavn Glacier, which is one of the two fastest flowing glaciers on the planet. The other's on East Greenland, and it is the Kangerlussuaq Glacier. One of the concerns with Greenland is that these melt lakes are becoming larger, and they are starting to form higher on the ice sheet. The problem with this water is that it runs along the surface, and where it finds a conduit called a moulin, the water will rush into the moulin. You can see that here in the schematic. And this water has the potential to lubricate the bed of the glacier. And if that happens, and you lubricate the ice-bedrock interface, then you have the potential for the ice to flow faster, and these outlet glaciers can discharge more ice. And that's exactly what is happening. This panel shows you, again, since the beginning of the satellite era, how the area of total melt over Greenland has increased over time. And in fact, in 2007, the total melt was 10 times greater than the previous maximum in 2005. But it is variable from year to year. And this shows how the melt extent is moving higher up on Greenland. And in 2007, my field team went in, and just to show you some images, let me go back. We went in here to drill in this zone where we're now just beginning to experience melt. And the idea here is to extract a multi-century record. The ice cores we drilled there will go back about 250 years. We are going to be looking at the melt record in those cores, among other things, to determine whether the melt that we're experiencing there now is unusual within a longer-term context. And so again, our shelters, and we were beset by quite a storm. And just to show you how small our equipment is, and this is our little field team, and these are the two young ladies who are receiving the scholarship this afternoon. So let me wrap up with just telling you a little bit about sea level rise. Over most of the 20th century, the sea level was rising about 2 millimeters a year. And about half of this comes from thermal expansion of the ocean. About 30% has been coming from the alpine glaciers. The ice sheets are contributing somewhere close to 20%. And we're getting a few percent from the pumping of groundwater for irrigation. Mark Meyer published a paper in Science last year saying that currently 60% of the ice on land that is going into the ocean is actually coming from the ice caps and small glaciers and not from the ice sheets. And that they would contribute about 1/4 of a meter to sea level rise by 2100. However, since 1990, sea level's been rising faster, about 3.3 millimeters per year. At the same time, many of the glaciers that are draining, particularly the southern part of Greenland and part of the West Antarctic ice sheet, have accelerated their discharge to the ocean. Some of these glaciers are flowing up to 100% faster. But this is very variable over very short time intervals, and our observational period is very short. The key question is, how are these ice sheets going to behave in the future? They're definitely the big gorilla in terms of sea level rise. We do not understand them well. Our models are very primitive. The major models that give the projections do not include fast glacier flow and unstable ice sheets. but that seems to be what we're beginning to observe in southern Greenland and in West Antarctica. So with that, I'm going to turn it over to Lonnie. He's going to pick right up and carry on. I've talked about the unique histories we get from the polar regions, but Lonnie's going to tell you more about the unique histories that we can get from the high mountain glaciers.
Okay, I've been fortunate over the last 32 years to spend a lot of time in the mountain regions around the world. And these are very unusual places. We've actually, these are the places where we've drilled, our team from Ohio State. And I want to point out that no other time in human history would this have been possible. With the technologies that we have today, our ability to move around this planet allows us to get into these very remote parts of the world. The Earth, we often forget, is a sphere, and because of that, 50% of the surface area is actually between 30 north and 30 south. And also, if we look at the fact that we have 6.5 billion people living on the planet, 70% of the people live in this area. So it's an area that we need to understand both natural and human-driven climate changes. Huascarán is the highest tropical mountain on Earth. And there's a lot of logistical challenges for drilling in these places. In 1993, we drilled this col between the North Peak and the South Peak. And the logistics are challenging in that you have to use porters. We're out of the range of aircraft. And so in order to get up there, you have to move 6 tons of equipment to the top of these mountain ranges. And often on glaciers, there are crevasses, like here on Huascarán. This is a 16-meter ladder. We took 6 tons of equipment up there, and 51 days later, we brought 10 tons, including 2 ice cores, drilled the bedrock back down this ladder. But the real reason I show this is to reduce competition in my research area. We've developed photovoltaic cells, power systems to drive the drill, and using this is an environmentally correct way to drill. There's no pollution, and we drilled 2 cores to bedrock, 168 meters, using this power source. And if you're working at 20,000 feet, you have over half the Earth's atmosphere below you. So these panels actually produce 20 to 30% above manufacturer specs. So they're a wonderful source of power. In these areas, we can get a very detailed history of the Earth, as we do from the polar regions. This is the last 100 years from Huascarán. And you can see the annual layers in isotopes, the annual dry season dust layers, and you can see the annual variations in nitrates here, which have to do with NOx emissions from the Amazon, upwind from this site. But the surprising thing here was the length of records. When we proposed to drill here, we were proposed to get a 4,000-year history. We actually got a 19,000-year history. We could actually go back and look at what the conditions were like in the tropics during the last glacial stage. And the isotope curve here is shown in blue. We have an isotopic shift of 6 parts per mil, the same that we see in central Greenland and down in Antarctica. If you look at nitrates, you can see they're very low during the last glacial stage, and the increase as you come into the warmer Holocene. And there's a lag of about 2,000 years between peak isotopic temperature indicator and peaks in nitrates. And we think this has to do with vegetation response time in the Amazon. And then the dust shows it was very dry. There was a 200-fold increase in dust in the late glacial in the tropics. And you can see this big event here 4,200 years ago, a very huge drought. So they give us a record for parts of the world where we know very little. I'm just going to show you one of these sites. 2003, we drilled the Quelcaya ice cap and the Corapuna in southern Peru. The Quelcaya ice cap is the largest tropical ice cap on Earth. We didn't know that when we started working here back in the mid-70s, but it sits right above the Amazon basin. Very logistically challenging, again, to get in to recover the record, but it has this very marked seasonality. This is a characteristic of the tropics, wet season, dry season, and that is recorded in the ice. If you get to the summit, this is the drill site, and Amazon's off to the right. And these are the cores that we bring out. And when you bring these back to the lab, just like in the polar regions, there's a history. And I just showed two of the parameters here. This is the isotope showing the seasonality and the every dust year. So they're very much like a tree in the history that they record. As you go deeper into any glacier, time becomes compressed, and you can actually see it here. This is 1520 to 1560. In this part of the world, the Spanish arrived in 1531. This is the first period where we have any written history from this part of the world. But there were huge cultures, the Incas and Mochi, and we can look at the conditions that existed on an annual basis back through the rise and fall of those cultures. So that gives us a chance to work with archaeologists and anthropologists. So this record actually goes back to 315 AD with an annual history. This is the isotope record, and you can see the little ice age that we know about in the northern hemisphere, the reduced isotopes here. You can see the medieval warm period, not so warm in the tropics. And this is the dust history, and we can see major eruptions like Huayna Patina. So they're very good histories of the past. Now you can take these from a global perspective, and if you take all the cores that we've drilled in the tropics in the southern hemisphere and in the northern hemisphere, and you combine them, you get this 2,000-year history. These are decadal z-scores of isotopes, and you can see the medieval warm period in here, and you can also see the little ice age. But what really stands out is the 20th century in this time perspective. If you look at our reconstructions of temperatures from the northern hemisphere, based on tree rings and observations, these curves look very similar. And yet the tropics, that's 50% of the surface of the planet. And what really stands out is what's happened in the last 80 years. Now, if you take this record to the U.S. Senate, you don't get much response. And so the best way is to show what's happening to glaciers around the world, and because you can see this. And if you start, I'm going to go very quickly around the planet, starting in northern Alaska, 100% of the glaciers in the Brooks Range are retreating in today's world. Here's a picture from 1958, and here's 2003. Southeast Alaska, this is the Muir Glacier in 1941. It was over 800 meters thick. This is what it looked like in 2004. And when you look at these, just remember, this is just water on the surface of the planet that makes its way into the world's oceans and leads to sea level rise. You go to the Himalayas, hard to find old photos. This is 2002. This is actually debris-covered ice coming down here. This is where it was in 1957. So it's been thinning about 2 to 3 meters per year. If you go to the Alps, we have older pictures, and this is 1903, and it's going to fade into 2005. So this is actually ice coming down here. So if you come to 2005, you can see where the glaciers are. This is another glacier in the Italian Alps, 1932, in the same place in 2003. You can go to Glacier National Park in our country. When it was formed in 1912, there were over 100 glaciers in Glacier National Park. We now have 26. In less than 30 years, there'll be no glaciers in Glacier National Park. You go to the Andes in South America. Here's a photo from 1896 in Patagonia, then the same place in 2001. So it's very large-scale loss of ice. The tropics, it turns out, are a very important place to look at change. If you look at the sea surface temperatures, this is the center panel here, you can see there's a lot of variability. And you can see that in the lower panel that precipitation in the tropics follows those SSTs. But if you get up to the 500, 600 millibar level in the tropics, it's very uniform temperatures around the planet. So it's very important that every glacier in the tropics is retreating. And where we have time-lapse data, we can show that it's actually accelerating. Whether you're talking about the Himalayas or Corycalis down in the Andes of South America or Kilimanjaro in Africa, you're getting the same response over these very large areas. In Africa, the oldest picture we could find was taken in 1912. These are actually glaciers. This is not snow, it's glaciers on the mountain. This is 1970. There's a canyon starting to open up. This is 2000 when we actually went there to drill, recover ice cores. And as part of our drilling, we had aerial photograph flown at the top of the mountain. This is the northern ice field, Furtwanger, southern ice field. And from that, you can make maps. And we can compare the maps that have been made back to 1912. The blue areas are ice cover in 1912, 12.1 square kilometers. The white areas are the coverage in 2000, which is about 2.5 square kilometers. And so over that period, we lost over 80% of the ice on Kilimanjaro. If you connect all the maps that have been made since 1912 and project it to the future, sometime before 2020, the ice fields on Kilimanjaro will disappear. Now, the thing that shows that it's unusual is in the ice core records themselves. This is the northern ice field. This is our drill dome. We drilled 3 cores to bedrock. The oldest core goes back 11,700 years. The lower 50 meters of a 51-meter core look like this. This is normal ice where you have bubbles distributed throughout the ice. It's when you have snow that becomes firm, that becomes ice. But in the very top, you see these elongated bubbles. This occurs when you have meltwater and refreezing. Had it occurred any time in 11,700 years, you would see it in the ice. And it's not there. So it tells us it's unusual. There's a lot of debates what's happening to the ice, whether it's sublimating or melting. Well, this is actually a lake bursting out of the side of the Furtwanger Glacier. This is water, so it's melting in today's world. This is in 2003. We've continued to monitor those ice fields since we drilled. This is the 2000 map. This is January 28, 2006, October 15, 2007. And the ice continues to disappear. And if you look at Furtwanger, which is the glacier here in the crater, this is what it looked like in 2000. This is 2006, and this is 2007. And unfortunately, if you put the amount of ice in 2007, it's right on track to disappear sometime before 2020. And this is what we think the last piece will look like sometime before that. And of course, when it melts, the history is gone. You cannot look at the past. We have been working for 28 years in China, in Tibet, and these are the places that we've drilled. Our most recent site here was in 2006, Nanunami. This is a very important place to look for climate change because it's a source of so many of the major rivers in this part of the world. And Nanunami here is actually the source. This is the Indus River. This is the Ganges River. And then the Brahmaputra River actually comes up and flows along the northern flanks to this area. So we need to understand what the long-term history has been in that site. There's some 12,000 cubic kilometers of fresh water in these glaciers. And these are the lifeline for millions of people downstream. So what's happening to the glaciers are very important. Nanunami is an impressive peak, just about 20 kilometers north of the Indian border. And if you make your way up this mountain to the Nanunami Glacier, then up on the summit, you can see the drill camp out here, and a person for scale. We drilled 3 cores to bedrock, 158 meters, and brought those cores back frozen. This lightweight drill that Ellen was talking about is extremely essential for getting up to these elevations to recover the ice core. Often you can actually see changes in the past when you're drilling. And if you're in a new part of the world where no one has ever drilled, there's a lot of excitement in the drilling of these cores. Now there's a real, logistical challenge of how you get the cores back. So we start out with porters and Sherpas in this part of the world, and you get down to the edge of the glacier, you're still about 3,000 feet above where the vehicles are down in the valley. And so from the edge of the glacier down to the trucks, we use the transport that's available in different parts of the world. In this part of the world, it's yaks. And these are insulated core boxes. There are 6 meters of core in each box, 12 meters per yak. We drill 500 to 600 meters, so you can get an idea of the herd that's required to move these cores down. Well, the first thing we do when we bring the cores back is we look for these thermonuclear bomb tests. These are records around the world. And these are the sites that we have drilled in China in the past. And this gives the dates in which we drilled. And you can see this is from the Soviet test, 62, 63. And you can see this timeline in all these cores. In non-UNAMI, it's not there. Nor is the Ivy test from 1951-52, which shows us that there has been no net accumulation on this glacier at 20,000 feet in the Himalayas since 1950. So these are really remnants of an earlier climate on the planet, and therefore the water resource issue becomes very big. If you go down to the Andes of South America, the longest documented retreat record of a tropical glacier is Coricalis. We set up a baseline up here on the ridge back in 1978. This is what Coricalis looked like. By 2004, you see there's a lake here. It covered 78 acres. By 2005, it covered 84 acres. It's 60 meters deep. And if you look at this pasture here, they're usually alpaca and llama grazing here. On March 23rd, 2006, there was an avalanche that came off here, fell down into the lake, created a mini tsunami, breached the natural dam here, and flooded the valley below. And why this is important is that this lake didn't exist until 1991. So this is a relatively new phenomenon. You can see the lake actually starting here. So in the first 15 years that we've monitored this, the glacier was retreating up this valley about 6 meters per year. In the last 15 years, it's been retreating over 60 meters per year. So there's been a tenfold increase in the rate that it's disappearing. The thing that we think is very important here is the fact that Ellen was talking about the IPCC projections. Those are surface temperature warming. Actually, if you look at a cross-section of these models across the Earth from 60 north to 40 south, you can see that that warming is enhanced in the tropics at the high elevation where these glaciers are sitting. So we think they're responding already to those changes. So glaciers, especially tropical glaciers, are the canaries in the coal mine for our global climate system as they integrate and respond to key climatological variables of temperature, precipitation, cloudiness, humidity, radiation. Global glacier retreat at the beginning of the 21st century is driven mainly by increasing temperatures, although regional factors, deforestation, and things can play a role in this. If you're a skeptic on this issue, you will say the problem with all of these pictures is they're 20th century. And sometimes you can find older pictures in these remote parts of the world. This one we found from a Peruvian photographer, Chambi, taken in the mid-1930s. This is the same place, Curiretti, in 2006. If you overlap these two photos, you can see it's not only the retreat, but it's the thinning, the loss of volume that's taking place on these records. Here's a quote from Sir Ernest Shackleton in 1915, what the ice gets, the ice keeps. He was talking about his ship, the Endurance, but it's true about ice. Anything the ice gets, it preserves. And as these glaciers retreat, there are things coming out of the ice that can give us a longer-term perspective of this change. And I'm just going to show a couple. This is what the margin of Kelkaya looked like in 1977. This is now a lake. In 2002, at the backside of the lake, you can see a person for scale. This is a 30-meter ice cliff that's retreating. We found a plant deposit right here, a wetland plant deposit, no woody tissue, perfectly preserved. This is what it looked like in 2002. You can see the ice wall has just retreated off of it. So they were very well preserved plants. And the thing that is really amazing is how fast ice can disappear. 3 years later, this is the same place. Here's the plant deposit. And as the ice has retreated, more plants are coming out. We have now over 50 collections from around the western margin of this ice field. And this is the plant that came out in 2002, the Stichia muscoides. It's 5,200 years old. Now that tells us this glacier hasn't been smaller than today for 5,200 years. Otherwise, this wetland plant would have decayed. They've actually been able to do DNA reconstruction on these plants. Other things coming out of the ice, Utsi, the Iceman. What's intriguing about this guy is he's the same age as the plants down in the Andes in South America, 5,200 years in age. And we know a lot about this fella. We know he was shot in the back with an arrow, set down behind a boulder at the top of the Austrian Alps some 5,200 years ago and bled to death. But shortly after he died, there had to be a climate event, very large climate event, that buried him deep enough so he wasn't exposed until 1991. Otherwise, he would have decayed or he'd been eaten by the bears that live in this area. So that kind of gives us some time frame to look at these records. If you look at the paleoclimate records, this is Bar Matthews' record from Spiliathim here in Israel. And this is the Kilimanjaro record down in Tanzania. And if you look at 5,200 years ago, you see this event. It shows up in both places. In Africa, this would be a cold, wet event. And if you look at the archaeological records, this is also a time where there was large disruptions and a lot of what we call cities formed around this time. So a major event. And so since 2002, these are the places where this event is now documented. And it has a lot of implications because 5,200 years ago, there were maybe 200 million of us. There's 6.5 billion in today's climate. So if we had a change like this, which is natural, it would have huge human implications. So if you look at the Earth at the 20th and 21st century, we're losing ice everywhere where we have records. So climatologically, we're in unfamiliar territory, and the world's ice cover is responding dramatically to those changes. Now the question is, how significant is this? If we lose 8% of the ice that's now on this planet, what would happen to sea level? To give you an example, if you lose 8%, that's not an alarmist scenario. This is the Gulf Coast of America. And if you lose 8% of the ice, this is what it would look like. So here we are today, 8%. That's a 5-meter sea level rise. Go to a city like New York. This is where we are today. Lose 8% of the ice. Looks like this. I was walking along the beach here. A 5-meter sea level rise would have a huge impact on Tel Aviv. If you go to the Netherlands, well, you can forget it because it's not going to be there. So these are very significant. Even though these changes are taking place in very remote parts of the planet, they impact us all. This is a photo that was taken in Northwest Passage this summer in August. And first time the Northwest Passage has been ice-free in recorded history. And you can see the polar bear sitting there. Unfortunately, he cannot speak, nor can he vote. If you go to these remote parts of the world, like the Kelkaya ice cap, this is a Quechua Indian that lives right below the ice field. Now, she has very little to do with the current climate change, but she has very few resources to deal with the changing environment also. So these are the people who are first impacted. So the key points made in our presentation today is that the 20th century is the warmest in the last 2,000 years, as recorded in low-latitude ice cores. In several places, it's the warmest in 5,000 years. Ice cores provide a unique information that extends our knowledge of the Earth's climate history. Climatologically, we're in unfamiliar territory, and the world's ice cover is responding dramatically to these changes. The observed rapid changes in Greenland and Antarctica are not predicted in our climate models. They assume a slow linear response to climate forcing. We are seeing a fast response. The glaciers in most parts of the world are rapidly melting, and their loss will impact 2 to 3 billion people, mainly through water supplies. And the valuable paleoclimate archive will be lost forever. Then finally, glaciers are our most visible evidence of global warming. They integrate many of the climate variables of the Earth system. Their loss is readily apparent, and they have no political agenda. And so finally, to end with a view of our planet, these changes that Ellen was talking about, the long-term impacts of greenhouse gases, these are long-term. But and when we talk about global change, unfortunately, nature's a timekeeper, and none of us can see the clock that we're working with. So with that, I'd like to close, and thank you very much.
Thank you very, very much. We are a little short in time, but I will allow 1 or 2 questions to questions if there are. If not, we will leave it for the panel. We are going to have a panel discussion later. And then I will call the next speaker, Professor Mira Bar Matthews from the Geological Survey of Israel. She is our paleoclimate person. And you showed one of her works, and I'm very happy that she could make it 24 hours on the way from South Africa to London. And I'm also very happy that we are joining forces. I am on the climate side, and she's on the paleoclimate, and we have a joint PhD student now. We are trying to bring together the data, at least for the Middle East, for Israel, for the last 500 years, which is unique. We have no data going back more than 100 years, 150. Mira, please.
I'm very honored to be here today on my way from Africa, flying over the Kilimanjaro and seeing how it disappears slowly, and flying to where I'm staying on my sabbatical in Bristol, where Professor Eglinton is from. And I have to say that I'm very familiar with Professor Eglinton, and
Mira, please talk to the speaker.
I'm very familiar with both Ellen and Lonnie Thompson work and Professor Eglinton, although I'm not working in the marine record, but his calibration of the Alkenon, which we will talk about, help us a lot in calibrating the sea surface temperature in our region. So I'm very pleased to be here today. Ellen gave a very good introduction to the climate, and which I'm very happy I don't have to do it. And when we talk about climate change, Ellen showed very clearly that the northern hemisphere is where things are happening. And a lot of people wondering what happened in our region. Do we see climate change in our region? And sometimes in low latitude, especially not when you look at ice cores, in mid-latitude, it seems that not much is changing. And I will go and show you how we can reconstruct the climate in our region in the past and what is happening today. And really, the things that are happening here are not as dramatic as we heard from the ice core record, but things are happening. And what I want to talk is much more about our region, because that's what I was asked to talk about. And I will talk a little bit about the interplay between semi-arid and arid past climate in the Eastern Mediterranean and its implication for the future. And I don't want to say the future because we are living at the future now. We're actually feeling what the future is telling us. So we are, where is the, oh, it doesn't move? Ah, no, it doesn't move because it's here. Okay. So we are kind of playing between what we know, a Mediterranean semi-arid climate with trees and rain coming in the wintertime, to an arid climate where we see a lot of dust storm coming in our region. So the question is, what is going to win? Where are we standing? Now, to tell you something about our region is part of much wider desert belt. If we didn't have the Mediterranean Sea here, we would have been a desert. We are part of a desert that extends all the way from Morocco to Arabia. We are located at the northeast corner of the much wider desert belt of the Sahara Desert. But because of the Mediterranean Sea, we have a very narrow strip where the climate is much more moderate. It's semi-arid Mediterranean climate. So if we look at Israel, 25,000 square kilometers, the green area is where the climate is moderate, where most of the population live. But as we move about 40 kilometers to the east, 25 kilometers to the south, we're already coming to the arid, hyper-arid region. And the question is how these kind of boundaries between Mediterranean, nice climate, and arid, hyper-arid played in the past and will play in the future. Most of my talk, although not all, I will talk about a different archive, which is the equivalent of ice core, but it's we have to go down. Instead of climb up, we have to go down. And we're looking at cave deposit, and they are also a very good archive of climate, because cave deposits are forming when rainwater interacts with soil and rock, and when the drip enter the cave, to the space of the cave, CO2 is outgas, and we have calcite, speleocene forming. And these layers of calcite record environmental parameters. They record the temperature, they record what the rain brings over, and they record what is the vegetation above the cave telling us. So we have a land recorder of environmental parameters. However, we have caves in various parts of the world, and in each part of the world, they record not just the global climate, they record also the local climate, and we have to resort to unravel where is the global signature and where is the local signature. However, to form this beautiful stalagmite and stalactite, we need rain, because if we don't have rain, we don't have water to form this speleocene, and we need this rain will enter the unsaturated zone and the groundwater system in order for the water to drip into the cave. So, exactly like the lecture before, here we need rain to form speleocenes. If we don't have rain, nothing will deposited. And for climate reconstruction, in our case, we use precise dating to determine the timing of a climatic event. We are now we are using usually the uranium-thorium dating method, and we use, like in ice core, oxygen, carbon, hydrogen, other isotopic systematic like strontium, neodymium, as recorder of paleotemperature, origin of storm track, amount of rainfall, vegetation, and origin of dust. So this, you already saw this slide, and we see what is the threshold until here between several glacial and interglacial cycle and what is happening today. And we saw the average temperature warming, and as was said before, this is an average. Because it's an average, we don't see the extreme cases. Now, what happened in our region? And in order to understand what happened in our region, in the Eastern Mediterranean region, I will take you to some kind of a climate journey in time and space during the entire region, from Mediterranean type climate to the arid and hyper-arid region, and see how the climate in our region have responded to global climatic changes. And we will ask our question, we will see, was this region always like this? Did we see always this boundary between semi-arid Mediterranean and arid, or it changed, oscillate in time? And I will refer first to time period that we're actually not living in today, but just to show you that we can use speleocene, and speleocene tell us things about our climate and about our environment through time. And I will take you to the time period between about 70 to 17,000 years ago, time period that the time which is referred to the Ice Age, when a colder period characterized the globe, an extensive ice sheet over the North American and Euro-Asian continent was much larger, and so the Antarctic ice was much larger. The question is, what happened in a region like ours where we never have ice coming so much further south? And I want to talk a little bit about this time period, so I can refer and show you what is the difference in the present climate that we're living on. So like in ice core, we also have a very detailed oxygen and carbon isotopic record that show large oscillation with time. Here we're looking at about 185,000 years ago, with the blue showing the glacial period, and here are the interglacial period. This is the previous interglacial, and this is the period, the last 12,000, what's called the Holocene. the period that it's more likely the present period. And we see that there were very large oscillations, and this large oscillation show us that in the Mediterranean region, we did see a very major climatic change over glacial and interglacial period. And when we look at the record from our region and compare it to the global record, here is the temperature, CO2, and dust component, we see that when we look at the Mediterranean region, we see the timing of climatic change correlate with global climatic changes. However, it correlates in time, we see the same amplitude, but the question is what this means in terms of climate in our region. And I want to talk about what happened in a totally different world in our region during the last glacial, when there were much more ice cover in the northern and southern hemisphere. And this is what happened in the Mediterranean region. We have spillocean forming through glacial and interglacial. So we can say that in the eastern Mediterranean climate, we always had water in the system because there is no hiatus in the spillocean growth. So we always had water. The question is how much water, how efficient did the water migrate to the unsaturated zone, to the groundwater system. And this is the picture from the east side, from the Jordan Valley and the northern Negev. Just about what is today 160 millimeter average rainfall. And during the last glacial, what we see, that in central Israel, we always had spillocean forming. We know from our proxy data that the temperature during this period was about 4 to 8 degrees lower than present. We also know from our proxy data that the rainfall always originated from, pick its moisture source from the eastern Mediterranean Sea. And we know that most of the time the vegetation was similar to the vegetation today, but during the glacial we had more expansion of grass of C4 type. This is true for central Israel. In the Negev desert, what you can see here is a work of our PhD, Anton Vax. It shows the frequency of spillocean growth. And we see that during the glacial, we had a lot more spilloceans in the northern Negev. During the Holocene, we have nothing. There is not enough rain. And during previous interglacial, we have much less compared to the glacial period. So we know that the northern part of the desert and the Jordan Valley received more water in much colder climatic condition. So we can say that during the last glacial, the rainfall belt must have migrated into the Jordan Valley and about 25 kilometers south into the northern Negev desert. So we had slightly more greener desert than we see today. And we know that we had the lakes much larger than the present-day Dead Sea during this last glacial. However, there is a pollen record that shows us that although there was much larger lake and although that we got a lot of spillocean, the vegetation in the region was semi-desert during this last glacial. This is the work of our student, Daphna Kadosh, who's sitting here among the audience. So, and the spillocean record also showed that during the last glacial, we have more C4 grass in our region. So we have a debate among the paleoclimate community. There is a mistake in the spelling. And the question that we will always argue was the last glacial wetter in the Mediterranean region, or because the temperature was lower, we had more efficient, we had a higher precipitation to evaporation ratio, and therefore we have more water in the system. When we look at the very south part of Israel, the hyper-arid region, which is the northeast extension of the much larger Sahara belt, what have happened during the last glacial? During the last glacial, we had nothing in this part of the Negev. So this part of our region, the very, very south, remained desert, desert during the last glacial. However, we see that during the interglacial, but not the Holocene, we have speleocene deposition in the very extreme arid region of southern Israel. Can you imagine you go now to the Negev desert, you go into the cave and you find this beautiful speleocene, this stalagmite and stalactite. To have speleocene in such an extreme arid condition, we must have had much wetter climate at that time period. So I showed you that the glacial world was slightly different in our region. The Northern Negev and the Jordan Valley had more water, were a little bit greener, but not the Southern Negev. The question is now, what happened during interglacial time? What happened today? How the landscape have changed? Because this is the time that we are living today. So we know that during interglacial time, we had, in the cave system, there were a period of a lot of water. In the Mediterranean Sea, we know this very known sapropel organic rich layer through several time intervals. We know that there were this period where we see the very sharp peak in the oxygen isotopic value, or here, the last one ended about 6,000 years ago. We know that there were much wetter climate here. And this wetter climate are associated with a lot of the floods from the Nile River. We had there was a period of higher insolation in the northern hemisphere, and the caves were extremely wet. And this period are associated with these events when the southern Negev was very, very wet. Apparently, our students just published a paper not long ago, and clearly showing that this period, very wet interval, about 125,000 years ago, are associated with the migration of the modern human out of Africa. So we can look now at the summary of the overall picture and see that in central Israel we had speleocene, we had water in the systems through glacial and interglacial. In the northern Negev it became more fragmented. We had some deposition during interglacial, and in the southern Negev this part had some wetter interval, and which we call them Negev humid period. But this wetter interval was not that wet to change the landscape. Still, soil wasn't developed in the desert, and we had very scarce vegetation, but they were wetter than today. However, and this period are associated with period of the intensification of the Indian monsoon, the Atlantic monsoon, and mid-latitude cyclones. But the question is now how this is relevant for the past. What are the future and the present implications? And as I said, during the Holocene, during the last 12,000 years, we have speleocene deposition in central and northern Israel, but nothing in the Jordan Valley, nothing in the northern Negev, and nothing in the southern Negev. So we cannot assume that the Negev in this present condition with warming and more evaporation will turn to be green. So we have to look at the climate variation in the central part of Israel, in the northern and the center of Israel. And we see that if we look at the last 6,000 years, there is a lot of variation. And as Lonnie said, this is the 5,200 year that in our region was a drought. Ice was melting in other part of the world, but here it was drought. So we have to think, we have to look at this association between melting of ice and drought in our region. So we see that there was changes, and we can actually calculate what was the changes. We know from a temperature proxies that we didn't see much changes in temperature in our region. And maybe there are changes, but the average temperature change during the last 6,000 years in our region is negligible. Maybe half a degree here and there. But the biggest changes in our region was the average amount of precipitation. And this is also the response of the Dead Sea to changes in average amount of precipitation. And we obviously see the early Holocene with much higher average and the drought at 5,200 years ago, the middle Holocene around the average, this is the average, and the last 1,500 years with many periods of precipitation below the average. And this is to do with natural changes. Now, on top of it, we have to add the anthropogenic influence. Now, in order to understand what happened in our region when we have an average change from 700 to 400 millimeter like this, we have to look at much higher resolution. What actually happened when we have such a change? Because this graph is an average, and an average is an average over 10 to 20 years. But 10 to 20 years, again, it's, for one person, it's a long time. So we look at higher resolution, and when we look at higher resolution, we look at annual changes, yearly changes. And for this, we have much higher sophisticated mass spectrometer. In this case, we look at a combination of SIMS with confocal microscopy, and we look at the lamination. And when we look at the lamination of a spilosome through a period like this, from 2,000 to 1,000 to 900 years, and this is a very important period in our region because we're going from the Roman to the Muslim time. So what actually have happened? And when we look at the high resolution, we see that we have a change in the lamination. And the change in the lamination means a change in the migration of the water. What we see here is a change. Here is a summer lamina, winter lamina, summer lamina, winter lamina. To have spilosome forming in the summer, it means that we had enough rain, so water reside in the unsaturated zone. And suddenly here, we are losing this lamination. Most of what we see is a winter lamination. It means that we didn't have enough rain to keep the water in the unsaturated zone during summer. And when we calculate and do it in high resolution, we do see that this was a very sharp change between 2,000 to 1,400 years ago. This is a period that we had rain, and slowly, the climate is changing. Here we are already in the Muslim period. The question is, what have happened? And what have happened is that we lost our water during the summertime as we reduced the amount of precipitation due to climate changes. Now, if on top of it we add warming, more rain is going to be lost due to evaporation. And if you look at the last 150 years, there are only 3 years that follow the pattern that we saw about 2,000 years ago. This is nothing. So what we see in the last 150 years, that we have period with much below the average, which we can see here, and these are coming and repeating themselves since 1993. And we also looked at some paleoflood record from the Negev desert, and we saw what we are reconstructing from our paleoflood records is when we had more extreme events. And associated with this change in the rainfall pattern between 2,000 and 900, we see that during this time period, we do see more flood, more extreme events in the Negev desert. So based on our paleoclimate reconstruction, what can we say about the future? And again, the future is the time that we are living now, because it's happening. It's happening now on a very short time scale. We lose water to the unsaturated zone, which means to the groundwater system in the region. It is important to say that we lose water in the environment where most of the people are concentrated, because I'm not talking now about the Negev desert, I'm talking about central and northern Israel. We have much more extreme events, and this should be expected. And from the work I'm doing now in Bristol, I didn't want to go into it because it's a lecture by itself. I'm working on other isotopic systematic on the strontium and neodymium, which tell us about the provenance of the dust. And what we see is that during the last 10, 15 years, we have much more evidence to the increase of dust from further away sources further away into the Sahara due to deforestation, and whereas before most of our dust came from some kind of local sources, we do get now much more input from further away sources from the Sahara Desert. So I would like to thank you here, and I hope that this won't control our region in the very next future. Thank you very much.
Thank you very much, Mira. I want now to invite our Dan David laureate, Professor Jeff Eglinton, and he will speak on biomolecular tools for paleoclimatologists. I want one comment to Mira, mention that we are really trying to work in future. We are running in our department here, within the GLOA Jordan River project, regional climate models. So we are running it now transit run by 100 years. And we compare to recent past, and we are going to about 2100. Professor Jeff Eglinton, I am very much looking forward to see your work and to hear you. Please.
You need to show me the gadgets, please. Which is this the button?
Yes, let me close this one. It's already here.
So it's
what's the name of it?
It's called the final tool. See in the bottom, that
This
one
one?
there.
Okay.
Thank you. So all I do now is press
You can press
Or-
here or press page down here.
the page down. That one.
Yes.
Okay.
I
Thank you.
think this should. Yes.
Well, ladies and gentlemen, it's a daunting thing to follow all these marvelous records. I did ask before I came here what you might think would be appropriate, and you told me that perhaps they would like to hear something of how the field that has developed came about. So I'm going to be somewhat historical, if not hysterical, in this account. So the first thing, I think, is that, as you can see from the title, I'm going to be talking about the molecular level rather than what we've heard of mostly, which is to do with the isotopes and element distributions, dust, and so on. But there are, of course, very major crossovers between all of these types of measurement. The second thing is that over the years we've concocted a number of little phrases and things that were, and this bottom bit here is supposed to be sort of chanted to the refrain of "Where have all the flowers gone?" So, where have all life's molecules gone? Recycled to carbon dioxide, every one. Ah, but look, a hardy few remain as biomarkers imprisoned in the fossil domain. Now, we'd like to sort of try to put that more into a picture in your mind's eye of just what does it mean? Why are we interested in molecules? After all, we're all composed of molecules around our bones, and you might think that this has really such an ephemeral lifetime that is not going to be much of a record. But in fact there is, and I think since we're going to be talking about marine records, my son number one suggested that I take you out in your mind's eye out across the ocean. I'm not sure which direction the ocean is from here, but we're that way? Yes, okay. But we fly out, and then I want you to sink slowly into the water surface. What you would see, I hope, is a fine spray of little green things floating around, which are the algae and so on. And you would also perhaps see a small amount of the Saharan dust settling into the water as well. So it would be sort of a shimmering, greeny blue thing with these particles. Now those particles are the primary production of the organic molecules that we're going to be talking about. Now then come down further in the water, and it'll get slowly darker. And as you go down, you will see that the nature of this material is changing, because the algae are being eaten by zooplankton, and the zooplankton are being eaten by fish, and these are all producing feces, some of which will descend relatively rapidly to the sea floor. Other rain will be of microbial colonized material. So already the initial imprint of the algae with their particular molecules is changing, but not completely, because even though the bacteria are operating in the fecal pellets and so on, and changing a lot of the things, using up the molecules, some of the molecules are more resistant than others and persist. So now let's go right down to the bottom, say 2 or 3 kilometers, and it's now completely dark. And there's on the mud at the bottom, if we could switch on the lights in our small sub, then we would see a very smooth surface of mud and a few things crawling around trying to find something to eat. And then if we could sink into the mud and then just sit there and leave it for a few thousand years, very slowly this rain of debris would come down on top of us and so create the sedimentary record. Now during that time, some of the molecules are actually going to stay there as quite well-preserved compounds. Others are going to be chewed up by the bacteria in the sediment, and they themselves then contribute their material. So gradually, as it compresses, this activity ceases or almost stops. And so now we have our sedimentary record of the molecules. Now, if we look at that, what will that record contain? Well, it will contain, first of all, a very small amount, 0.1%, 0.01% or something like this, of the initial primary production of molecules like chlorophyll, carotenoids, sterols, and so on. We'll also have a small amount of hydrocarbons and fatty acids and so on that have come in the dust. For example, from your C3 and C4 plants that have been blown out in the dust. And they're all in there. And in addition, there's a lot of this microbial, viral, and other debris. So you might think that's the most impossible thing to analyze. Well, of course, it is pretty difficult. But not only is it possible to look, for example, in the younger materials at the DNA molecules, some of which are partially or fully preserved, but it's also possible to look at, say, the protein and sugars and so on. But above all, and this is where we came in because of the nature of the molecules, the lipid composition, in other words, the fatty composition, think molecules like cholesterol and so on, and the hydrocarbons, these are much easier to separate and to analyze, and that's how we got started somewhere in the early 50s, 60s time. So there is the background to that little, well, I won't call it a poem or anything, but it's a phraseology. Right, so let's, first thing that I wanted to do then was to say something about the enormous number of people being involved. Well, one way I could show this is really just to show you the people, first of all, who helped put this talk, I mean, where I've stolen slides and so on. Everybody knows this technique. It's getting much easier now with the internet, of course. But then, secondly, we have here a listing, which I compiled just recently, of all the PhD students and MSc students who've been through the OGU, the Organic Geochemistry Unit at Bristol. And it is quite extraordinary, and I'm very proud of it. But it actually falls into two halves, because there's the first half, more or less, down to about 1995 or so, where James Maxwell and I were the supervisors or advisors to these people. And then since then, when I retired, the unit has been run by Richard Evershed and Richard Pancost. And this is an extraordinary combination, because Richard Evershed deals mainly with archaeological evidence. For example, he's just had a paper accepted in Nature showing the earliest advent of dairying in the world, as from the evidence they have, which is on potsherds, the small pieces of pot. You analyze this, and by the lipid molecules, you can see that, in fact, the dairying was being used. So that's his area. And Richard Pancost is more interested in paleoclimate, and in fact, really ought to be giving this talk, I think, rather than me. So that gives you some idea. And then on top of that, there are all the visitors who've come to Bristol from all over the world during the time, and what fun we've had working on all these things together. So here is the sort of theme of the thing, that life leaves these molecular residues, like I've tried to picture for you, and they can persist for literally billions of years. The oldest sort of molecular evidence we have, mainly from the work of Roger Summons and others, is somewhere around about 3 to 3.5 billion years. These are molecules that we can recognize as being biological in origin. They've been battered around, and somewhat a great deal of attrition has occurred, but they're still recognizable as these fossils. And then not only do you identify them by their molecular structures, which is the realm of the organic chemistry, and we're going to see that in a moment, but you can also use their isotopic content. So there's a tremendous amount of information in these molecules. And that really was the most exciting thing to get to. Once we started, just out of curiosity, to look and see what was in rocks, then suddenly to find, lo and behold, they really are interesting compounds there, and they have a story to tell. Now, this is the sort of creed of the whole of biology, more or less. I mean, one can easily find ifs and buts, but the main idea is that the most information content of all is in the DNA molecule and in the RNA. Proteins, then, are specialized bits of high information. Proteins that do very specific things, or more general ones that do a sort of a number of jobs. And then finally you come to the smaller molecules, the metabolites, the sugars, which can lipids and so on. And it's the lipids that we have to use as some reference point back, in a way, to the DNA. Because most of the DNA is destroyed very rapidly. It falls apart or taken apart. And only in special circumstances, such as in ice cores, as we've heard, or in highly anoxic sediments, you get a much better preservation. Also, another thing that's interesting, following on from your talk, is that caves are a very good place to find molecular evidence. The constant conditions, relatively speaking, are ideal for holding things. So, there we are. I'm afraid we have to concentrate on lipids, and then we can say, then, there's a whole story here which we don't have time to do. So what I'm going to show you a little bit about what they are, what our molecules are, and if there are a lot of non-chemists in the room, that's fine, but if there are some chemists, I apologize for doing a bit of chemistry in a moment. And so we won't deal with how we analyze them and so on, but we are going to look at who and what made them, and a little bit about how they get there and so on. But then after the bottom one, we come to really what is the use we can make of them, which leads on to the possibilities then of how they might help us with the future. So here's the chemistry coming along now, it's a beautiful picture of course, something which we've never seen, but we would like to think it might look something vaguely like that. This is methane, and as you can see, the type of diagram on the right, which we're going to see expanded, the hydrogen is towards you on the front one, and then the dotted line means that that one on the right is away from you. That's all that terminology means. And then the key thing about isotopes, it's extraordinary how much information can be found in a single molecule with one carbon atom like this, because you've got 3 carbon isotopes and you've got 3 hydrogen isotopes. Well, of those, the C13 is very useful because it's a stable isotope. The C14 has very specialized uses, we have a little about. And then the hydrogen, again, the deuterium, the H2, that is also very useful because that's stable. And so this talk won't have anything about the tritium on the right. So a lot of scope there for information. But now we're getting on to move into the molecules higher. Then if there's the diagram I showed you for methane, now here is a diagram for a 29 carbon hydrocarbon, that sort of spotty looking thing along the top. They're very wiggly, but they do like lining up in straight lines and when they crystallize. So if you can imagine a crystal, say, of a rather pure candle wax, you have a lot of molecules lined up like that. They're flexible, so they're used in biology for quite a number of things. Particularly the plants use them as the protective crystals on the surface of all plant leaves. And there's the line drawing. I would like you to look at that because that line drawing means you've got 29 carbons linked together, all coated with the appropriate number of hydrogens. Now, let's get to a more exciting molecule. This is chlorophyll, and you can see there's a hydrocarbon chain on the end at the right. It's this phytyl side chain, and the ring in the middle, I think there was one of these weapons around here somewhere, laser point. Is that the thing?
Just use this.
Is that a...
That one right there.
Right, thank you. Oh yes, here we are. Here is the magnesium in the middle, and the 4 nitrogens around, and the oxygens here. And here is the line diagram for the same thing. So why I've shown you this is that this ring, with all its conjugated double bonds, in other words, electron-rich, is actually like a sort of antenna which receives the sunlight. And this part, the hydrocarbon part, is really a sort of handle, if you like, for the antenna. And they all pack together, so it makes a very beautiful thing, which the chloroplast is in the plant cell and acts as the energy receiver for photosynthesis. So there you have an important molecule. Now, the unfortunate thing about that, from the point of view of the geological record, is that a molecule like this will fall apart at this bond down here, this ester link. It'll also lose these bits pretty readily, and the double bond tends to get hydrogenated, and the magnesium gets lost. So you might think, well, that's it. But in fact, what's left is still very useful as a recognizing tool for the photosynthetic molecule, chlorophyll. And the side chain is pretty tough, so that turns up too in the geological record, and we'll see that in a minute. Now then, moving on to the global scale, then we now have these marvelous assemblages from satellite data, and this shows then chlorophyll distributed around the globe. And what's the extraordinary thing you see right away is that the chlorophyll, which is this yellow-red in concentration like that, and here, and here, and here, this is in the cold regions. And of course, here's the cold regions and the SST composite, all these blue parts. Just look at the Gulf Stream coming across here. you see that this little green, paley, in other words, colder part here is where the chlorophyll is being produced here. And similarly down here, and down here, and down here, and down here, and so on. So why is this? Well, it's the upwelling systems of the cold nutrient-rich waters which are coming, and they're being driven by the wind systems. So immediately we see just what an incredible business of interlocking and feedback loops that I mentioned last night in controlling all of this, which, I mean, is incredibly important because, of course, all our fisheries depend on the production of the chlorophyll in the way I described earlier. So if we could, say, look at a map of, just like that, of fossil chlorophyll, that would be a really exciting thing to have in the time frame. Also, we can, if we had a map, a global map again, say, set at 12,000 years ago, of the sea surface temperatures, this would be an extremely useful thing for understanding the climate at that time. And so what I'm going to try and show you then is something about the way we would get there. Now, there was some muttering about me as either a father or grandfather of this area. Actually, the whatever grandfathers were should be attached to this name down here, Alfred Tripes, in Germany, who first of all noticed that if he extracted oil, certain petroleums and certain rocks, you could obtain red pigments. And he showed that these were their sort of structures. These porphyrins here. Now you can see immediately the similarity between these two fossil molecules that he found and the molecule of chlorophyll. The magnesium has gone and been replaced by nickel, and various other changes I mentioned have occurred. So here is the, excuse me, the pristane and the phytane that I mentioned, which comes from this side chain here, also found in. This was somewhat later that we found those, but what you can see is that you can have a biological precursor, and you can find the fossil molecules which match that. But sometimes the excuse me. Okay. Sometimes the molecule is unchanged. It survives intact from the beginning to the end. And we make use of that, as you'll see. So there's the science in a nutshell. I've more or less said all this already, but the information sources is the key thing. We've got to be sure we got the right molecules, and that's a lot of fun for us as chemists. And then when we've done that, we may even be able to do the isotopes, and a lot of that has developed in recent years. People like John Hayes revolutionized the whole field by showing that you could measure the C13 in individual compounds rather than take a job lot of, say, organic matter in a soil. So what does their presence tell us? Well, let's see. We've got the molecular structures, we have the relative and absolute amounts, and we have the isotopic composition. So, over the recent years, quite a number of compounds have been found as what we call proxies, as mentioned earlier on, for certain types of happening. Now, they're like all proxies, they have their faults and their good points and so on, and we can't go into all of that, but just to show you that these are some of the things that people are now talking about. So there's wind systems, the dust transport can be followed by these plant waxes. There we are, over here. The CO2 pressure can also be estimated by using alkinone delta C13 data, though that has problems, but it still has been demonstrated to be useful at certain times. In terms of the continent, then you have, I won't go into this, the soil temperatures, but there is a recent proxy being proposed for that. There's the hydrography, of course, in the plant wax, delta D. That's where, when the plant waxes were made, then the hydrogen that goes into the wax has to come from the water. So you have the imprint of the deuterium in the groundwater or in the water of the falling on the plant gets incorporated into the plant wax. And there's the C3 versus C4 technique also. Now then, this is really what I want to concentrate on. This is for past oceanic conditions. And there are now a whole host of exciting things that can be looked for. And you might be interested in, when you're a scientist developing things, people mutter away about, oh, that's not very interesting, or you've got it completely wrong, or whatever. But the one that got me most was one colleague from San Diego listened to what I was talking about and said, he said, all you're doing is collecting stamps. And I said, yes, but you geologists have been collecting stamps for years. Fossils you had to do to get the whole concept of stratigraphy, etc., etc. So, I felt I'd beaten him off. But the result of the stamp collecting is that gradually you find out what the stamps mean. And in this case, we now know that these molecules we found first and get very excited about perhaps have a real meaning. Sometimes we knew what to look for. But many times what we did, we found molecules that no one had ever seen before, and people said, what? Where on earth have these come from? Well, that starts off a whole new type of research. Anyway, that's enough for a philosophical discussion. I'm going to talk about this one, SST, sea surface temperatures, the molecules called the alkenones, which you were kind enough to mention earlier on. So, there it is. I've called it a convenient molecule, which I thought might be appropriate for this conference. It is a molecular proxy, we now know, for sea surface temperatures. And what I'm going to tell you is just roughly how this happened, because most things in science, I firmly believe, are not planned. They sort of happen. We listened with great interest yesterday to Sir Tom Stoppard saying something like that. Anyway, here they are, the C37 alkanones. Now, I've trained you how to read these diagrams, so I'll just reinforce that if I may. Here we have a long chain of 37 carbons. It's pretty big molecule as far as we were concerned. And it has one oxygen, well, a ketone group here, and it has, in this case, 3 double bonds. There they are. And this is what it would look like if stretched out as a model. It will, of course, be somewhat flexible, but the double bonds reduce this flexibility considerably. And we think that may have something to do with their purpose in the organism for controlling their response to temperature. Anyway, there are 2 key molecules, and they may look identical at first glance, but this one has only 2 double bonds, whereas this one has 3. And that has good brownie points because, sorry, that's an English expression. They have good points in that if a molecule looks very much like another one, it's probably going to behave much like the other one. So therefore, when things are eating them, they may survive in parallel, if you see. So that's useful like that. On the other hand, you don't want them to be too close, otherwise you may not be able to distinguish them readily or separate them. But these work very well. And they're nice, tough molecules because they're long hydrocarbon chains. Now, that's what they occur in. E. huxleyi, Emiliania huxleyi, which is about 2 microns or so across. And these are calcite scales on the outside, which the thing makes. And nobody seems to know quite why. But they're like tiny little glass balls in the ocean in huge quantities, as we'll see. So under the microscope, these are from Plymouth, beautiful pictures. Here is one of the E. huxleyi cells, and inside that then is the algal cell, and this is it seen in transmission microscopy. These are the calcite scales partly seen here. This is a lipid body, in other words it's a fatty body, and it's known because of the staining we use with uranium and so on. And what you notice is that these blobs are all over the place. So this is where the alkenones are. But we still do not know precisely what these molecules do. The nearest that's been come so far is that they are storage lipids. Why should they change then with sea surface temperature? I don't know. It might be to do with a minor effect of density. It's difficult to tell. But anyway, that's you can see the chloroplast here with all the chlorophyll molecules in it. So there we are. There's our source organism. Now, we didn't sort of find this just like that. Anyway, this is a satellite picture showing, as you can see here, Nova Scotia here and Canada way beyond. And this is a bloom of these minute organisms. And there are many, many satellite pictures where you see this all over the world. It's incredibly widely distributed. And so it's useful. Did I perhaps go? Yes, I thought so. I missed one. Now, that shows you how widely distributed they are, because this is a composition of sea surface calcite made using optical satellite measurements. And here you can see vast blooms of these algae all over here. Here's this one off Nova Scotia and so on. The areas that are not showing these white patches still contain small amounts of these algae, and we find the alkanones in the sediment just the same. So what we're seeing here is that what we're going to come to about it being a sea surface temperature recorder means that we can actually measure the sea surface temperatures virtually anywhere on the ocean area, because there are sufficient alkanones present. So now the little historical bit, which I hope does interest you, but I hope I don't bore you with it. But this is just how one proxy was found. It's a curious history, because up here in 1967 or so, two more or less separate observations. One was that the North Sea sediments contained waxy or oily materials, and there was a big thought that they might be due to all the oil drilling in the North Sea, which turned out to be wrong. And then in parallel, Corner at Plymouth here, and his colleagues, they found that there was an alga, Emiliania huxleyi, which produced quite a lot of this oily material. And then this was put together and realized that these algae were probably the source of these North Sea sediment oils. Anyway, John Wokeman, when he came to Bristol, tackled this and separated them, and which was quite a job actually at the time, and partially characterized them, which means got their molecular structures more or less. But we had a visit from Jan Leeuw from Holland, came in the laboratory and said, "Good God, where did you get those?" Looking at the molecule evidence, the mass spectrometry. And so then we realized that these molecules had already been found in certain Atlantic sediments. So we got very interested in these things, and Simon Brussel, who was a student with me at the time and later on a postdoc with me, he started to find these alkanones all over the place. So we got even more excited, and my colleague James Maxwell actually then synthesized them to get the precise structures. So everything was then tied up. However, we had this sort of information. This is the gas chromatography trace, and so you have, these are the peaks. This is the 37,2 molecule, and that's the 37,3, and the one drawn down below here, you've seen already, is the 37,2. So this is how we analyze them, these two peaks. And when we started to do this, more or less routinely, Simon Brussel found that the sediments he had from the Japan Trench, which is an incredibly deep trench off Japan, where the waters above are very cold, 14 degrees centigrade average temperature, compared with 21 over here in this area, Middle American Trench. He was seeing these consistent down the course. So it wasn't just at one time, like now, that these signals were different. They were different systematically down through time. So he came, one day, Simon never bounded, but he came in rather quickly into my office and said, I found something really rather weird. And, you know, we both got quite excited about it. It was because he came up with this thing. Was it possible that it was to do with the temperature of the water? It wasn't anything to do then with the sediment itself. It was to do with the surface temperatures where the algae we now knew that made these things, because they're very unusual molecules, were living. So we might have a biothermometer. Well, as I say, this struck a chord when we heard Tom Stoppard talking yesterday, that he described that when you're at the cusp of creation, he said, you think, you get all excited and think, God, that's it. And then you think, oh no, this is a tragic self-delusion. And I think we've all had this in any walk of life, whatever. But, I mean, that went on for months while we did it. You know, was this something to do with the analysis? Was it decay in the sediment? What was it? Or could it be that he was really right, that the temperature was it? Did we have a biothermometer? And we've been looking for something like this for a long time. But we never thought we'd have the chance. So anyway, we formulated this, and we had great fun with this, UK37, because we thought we ought to have some sort of symbol for it. So we thought U for unsaturation, K for ketone, 37 for chain length. But more than that, it was UK. So we thought, that's going to really especially annoy the Americans. So we did that. Of course, later on, a few years later, we had an American colleague come, Maureen Conti, and of course she wanted to have AA for hers. So the first calibration then was done by growing the algae down at Plymouth, and we had about either 3 or 4 spots. It was quite difficult to do these things at that time. This was done by Ian Marlowe. So we plotted that and said, it's looking pretty promising. But we then tried to find sediments from all around the world, and we started to collect them. And we got a sort of rough graph, as mentioned on here. There's, I think we must have missed one again. No. We then found that Simon Prowl, who had been at Bristol, went to Woods Hole and there got hold of these data for sediment trap material that's in the ocean. You have a sediment trap, and also from filtered material. And they put this calibration in, and that calibration has more or less stood the test of time. There are much more elaborate analyses now that have been done, many, many sediments and so on, but that's essentially it. So that is how it happened. And we then went on to see what we could now do with it, because after all, that's what we were really after. This came about through me spending a number of nights at a committee of DSDP down in the Barbados with Michael Sondheim down here, and he, for the first time, explained to me about the ocean isotope records and about sea surface temperature thing. And why should sea surface temperature be important? I hadn't thought about it before. So I came bounding back, and we went into making a trial with them. So here's our test area. Michael suggested the Cane Gap region, where there was a sort of nice area where the sediment could come down without getting swept away. And secondly, it was in a reasonably productive area. Here's the chlorophyll, and you see you're on the edge of the main chlorophyll upwelling region. It's also quite a nice warm site here. We're not too hot and not too cold. There are the Canary Islands, by the way, over here. Oh, no, they're not. Sorry, there's the Canary Islands. These are the Cape Verds. There's the prime upwelling region, as you can see here. Very, very cool. So we did this, and of course it was a pretty sort of staggering attempt because it was quite hard to do these analyses at the time. And we got these curves. Well, when we looked at that, we at Bristol, we couldn't really. It looked to us like somebody walking rather drunk down the road. And then when Michael saw it, he said, "Oh no!" He said, "Look, I'll show you this, which we hadn't seen, which was the 018 data for the foraminifera." Now, it's true, of course, that the 018 has two things in it. It has sea surface temperature, and it also has ice volume, what we've heard a lot about. So the two things are in there, whereas, as far as we were concerned, if we were right with our whole ideas, then this was a pure measurement of sea surface temperature, a molecular one, completely and utterly independent from the isotopic data. So that's one nice thing about a proxy. If you can get two proxies that are completely independent in their sort of origin, then that's rather exciting. So we then went on to look at a more detailed study with the Kiel group, and we chose this one, Site 658, which was an ODP, which meant that one of my people could go on the ship and suffer all the indignities of 2 months locked up with all the others. And it was an ideal site in the upwelling area, high productivity, a lot of sediment from the Saharan dust. And so it means then that the alkinone record of year by year of sediment from the algae is being strengthened, if you like, or widened by all of that dust. So that's the site there, the 658. Now it's in a much more chlorophyll-rich region, but also it's a cooler region here. And it might also show more temperature variation as the upwelling moves, perhaps, with the wind systems. So that's what we got. Here is the 018 record, which is the sort of, if you like, the professional record, and here were the amateurs coming along with our alkinone thing. And what we did, we began to find extremely sharp, when we put samples close together, we found major ups and downs. So we got very worried about this for a start, but we also got very excited. It was again the Tom Stoppard moment. And so we measured several regions in great detail. I mean, it's a slow business. So here we did another one at this termination of the ice age, and in here as well. And what these showed was that we had systematically major shifts of the order of 100-year time frames that were really very surprising. Well, when we tried to get this published in Nature, first of all, the referees turned it down and said that these temperature shoots are just crazy. There's nothing like that known. And so, go away and measure it again. So we went away, measured things again, and we came back with the same results, more or less. So this time it was accepted. So that's another little bit of history about how things happen. Then, if we now go on very quickly into the more recent times, here is a most beautiful example from one of our colleagues once upon a time, Grimald, Joan Grimald, who's at Barcelona, and his colleagues. And what this is a very continuous high resolution, in other words, sampling every few centimeters over a considerable portion of time. And this one is in the Mediterranean. And it matches well the Greenland ice record, and the time intervals are being chosen to give a reasonably good record, as you'll see. So first of all, there's the site, ODP 977A, right inside from Gibraltar in this region. And you notice, you can see the cooler temperatures here in the western Mediterranean, which is associated with the Atlantic. And here are this is the trace they published. Here's the UK 37, and here's the 018. You notice how remarkably similar they are for a start. So that the ice volume component is not really a very upsetting thing. And so we have abrupt warmings of around 10 degrees C, and we'll see those, I hope, if I press this button. Oh yes, there it comes. This is miraculous stuff done by somebody else. There's the very abrupt warming here as an example, but there are a lot of them along here which are rather less dramatic. And I mean, that's 10 degrees C per kilo year, and that's happened a lot, not just the odd time. Now, I mean, to an ice core person, all of these must look awfully woolly and rather indeterminate. But, I mean, remember, this is sea sediment record, so we've got all the problems of settlement and turbation and so on and so forth. But it's telling us something completely separate from the ice cores. It's ocean temperatures, and so they are doing the same things as the ice cores, which is rather gratifying. So the other thing is that in this lower trace, and this is something which is they found more or less for the first time, that there are a lot of spikes of this particular alkylone, 37,4, which I haven't fussed about so far, but that's got 4 double bonds. And that's associated, particularly, we now know, with cold, very cold waters and also low salinity. So what we notice is that these things are appearing, these peaks like this, more or less in parallel with Heinrichs, although they're not all lined up with the Heinrich events. Now, the Heinrich events are the melting events in the North Atlantic of the icebergs. The implication here is that we have pulses of low salinity cold waters, some of which must be coming from the Atlantic as a result of being in time with some of the events in the melting events in the Atlantic. Others will be to do with rivers and so on. So that's a quite dramatic thing. There are 2 completely bits of story here: the general sea surface temperature record and the 37.4 telling us about these low salinity pulses of cold water. Then the final one I wanted to show you is one that's just come out, and this is coming from the group led by Marisik here, Geosciences, and that is a record of northwest Iceland, which is for the last 2,000 years. And now remember, we're dealing with sediments, so we're not dealing with nicely settled layers of ice like you have, but it's still quite remarkable what comes out of this. This is where the record is from, just up here. And this is the temperature thing, so you can see it's in much colder water here. It's also at the junction of a lot of currents. And so you have the interesting idea then that these molecular markers can perhaps also tell us something about the current history of the global oceans, which would be a really exciting thing to get into, and there's good reason for thinking one can do a lot more along those lines. And here is the record which they've just published. So we are living up here, and here's the little ice age. Here's the temperature, sea surface temperature here. You can see it's been dropping like that from the medieval warm period, which is here, and then the Dark Ages were also rather cold, and then there's a warmer change that took place around Rome times. Now, the curve which is in light color is the actual UK 37 record, full of sharp changes. Now, they've smoothed this to show the general trend, but you would have to ask, then what about these sharp changes? Well, this is what they've described as rapid decadal now, scale variability of around 2 degrees C, and that's occurred for the last 2,000 years. I mean, it's a considerable effect. How much it's to do with the currents is, of course, one problem, the mixing of those, but anyway, this would certainly affect the climate very much, these sharp changes like this. Now, the longer-term warming and cooling trends certainly fit with the historical evidence and also with all the other that's gradually being gathered. So the real question then comes at what are all the forcing factors giving rise to these very sharp changes and also the longer-term trends? And of course, we then get into the big debate about what all is going on. Then, just to finish off, dealing with one small family of molecules, but they happen to be ones made by very few organisms and are very, very specific signals. What else can you do with them? Well, you can measure the stable carbon isotope, which I've mentioned, it will give you PCO2, and also it's a nutrient proxy to some extent. You can measure their radiocarbon content, and son Timothy over here has been doing a lot of that. And this shows some remarkable advection stories that I haven't time to tell you, but he might be able to. And then you can measure their deuterium content. Now, just like the plant waxes record the water around the plants, these molecules which are being formed by algae bathed in the ocean, the hydrocarbon chain of the alkenones is, of course, picking up the hydrogen from the ocean waters in the surface where they are made. I mean, they're not made down below, they're made where the light is. So we have, therefore, a history of deuterium that can be read. That's only just starting now, because the method was previously extremely difficult and has been, again, revolutionized by people at Woods Hole and elsewhere. These ocean surfaces do vary quite a lot in their deuterium, depending on the income of things like the St. Lawrence or the Gulf Stream, or just simply all the precipitation which is coming and it dropping out water as it goes along changes the isotope content. So there's going to be a lot of scope for this, I think, in the future in looking at past oceanic conditions. So I sort of started getting a bit, philosophical here. Rosengut, Stanson, Guildenstern are dead, but the alkenones live on. So here we are. They can be used to generate, we know, paleo-SST records at high time resolution. We've seen that when the geological conditions are right. They're virtually ubiquitous in the lake quaternary sediments, so we've got a lot of work that could be done. But particularly, I would like to flog the idea that the global paleo-SST maps, if one could create those with some confidence, then you can feed them to the modelers and say, well, there you are. Those are the real temperatures of the surface of the oceans. How does that affect your modeling of the climate? And hence, you can then do the classic thing of going forward. So there are the future challenges, I think, in the 1800s, 1900s, people were having a great time doing the stamp collecting. And they would say, well, what is there? And that was natural history. Darwin essentially was a natural historian who had a brilliant intellect and capability of seeing what it meant. Then in this last century, we've really had just how does nature work? Everybody's studying it with all the tools they can get at. And even how can you change it, for example, modern medicine and so on. Now we're into this next bit. We really want to know how this planet works. We think we've found out the basics, but I wonder how to care for it. I did have the word manage, but we some arguments over whether we should think of managing things, but so I stuck this on the bottom. So I know there's at least one young scientist who is there, another one here, and so on. So all I can say is, the tools are there, so go for it. But when you think of actually getting to the point where giving advice to government, they say, what do you do? What should we do? We don't want to do what you think we should do, but what should we do? Then comes the question, you think, now, it's a very complicated system. And my only advice was, yes, go for it, but for God's sake, be careful. Thank you.
Thank you very, very much, Jeffrey, for giving me at least a sense of this exciting research, which I'm not familiar with. We are going to our last talk of today. We are a little late, so with the panel, we are going to leave, I hope, few minutes for questions. Professor Boaz Lazar is our last speaker. He's from the Hebrew University, the Institute of Earth Sciences, and he's our geochemist, talking about biogeochemical processes at his work. Let me make one comment about the SST importance as a climate modeler or atmospheric researcher. We know that the SST is extremely important in forcing the atmosphere. We know it from sea breezes, etc., but from climate, we know it's very, very important.
Okay. So thank you very much. And first, I would like to congratulate the laureates here and thank the committee to invite me to speak here. Specifically because what is term is a long term is really maybe a few decades and not several 100,000 of years. And but what I hope to show you here is that not to look at really the proxies, but to look at the parameters themselves, how they look over that time, and to see if we can trace a perturbation which is made by humans, and maybe even to correct it. So there is still hope, as was just said in the last in the last slide. So while we are going up and zooming into the area down, I would like to show that you will see all these names, because actually this work is a work of many people, that everyone did his part, and what we take and do some of the compilation only. And it was also founded by several large projects which are listed down here, from Germany to US and Israeli, and all of them together gathered this data. So it's really me to present it, but it is not only a single work. Anyway, if we go to this area and we look at it, we see that this part that we are dealing there is separated from the open ocean by two seals, which are shallow seals. This is actually, for an oceanographer, it is a filter, because it lets only surface water enter to this system. Even the depth of this and these places is pretty deep. This is 2,500 meters, and this is 2,000 meters deep. So it is an oceanic water body, but it is connected only through surface water only, which for an oceanographer tells it low nutrients are coming in. Okay? And in that sense, the flow here, as was said already by Mira, it is a big and vast desert area, and the flow is controlled by evaporation. There is nothing, almost nothing coming as fresh water, virtually nothing, and excess evaporation drives the flow in. So the water comes basically, and then they go out also, but that's the control, and the residence time of waters here in this area, and this small thing is about 2 years, in the whole system is about 50 years. So it's a pretty dynamic system as well. Okay, now if we again zoom into this area and we look at the section, this is a cross-section from here to here, and again, waters are coming in, driven by evaporation, and goes up. What leaves the salinity inside higher than the salinity outside. And if we look at this station, that we do lots of measurement there, because what can we do now? Our sea at the Red Sea is only this part, so that's the southernmost place that we can do really comprehensive work there, is right here. And if we see how this behaves on a annual scale, so if you look at the temperature versus depth, which tells you how the water column behaves, and you see how it goes. It is cooling, and you have a mixed layer forming, and mixed layer, and then it is mixed, and then it starts to warm up, and that's a cycle. But, and then if we want to look at other parameters like nutrients and chlorophyll and temperature together, I will not go into that in depth, but let's look only at the nitrate as a nutrient. And what you see that during this mixing and stratification, you have that the nitrate is very, very low at surface water, at the photic zone. And even during mixing, it stays low because the phytoplankton can cope up with this mixing and the nutrients that are bringing from the deep water up. But when the mixing is very deep, then the phytoplankton cannot cope with this input of nutrients, and it leaves relatively high concentration of nutrient also at surface water. And this is very important to recall. And by the way, if you look at the chlorophyll here, you see that even at 700 meters, you have a viable chlorophyll. So the mixing is so intense and so fast that the chlorophyll, you take algae from here, it will still be viable. Okay. Now these mixing events are not the same every year, and that's very important to see. That's all the thing that I could gather. It is since 75 up to this year. And you see that that's the depth of the mixed layer at this station, which is this is the depth of the station, but we sometimes measure also in other stations, so we know the mixing depth. And you see that the mixing depth goes really down to the bottom, not so many times. But then it is really an important sign for us as oceanographers, because when the mixing goes down to the bottom, then you have a reset of a system. The system is completely mixed, reset, and then you can start and follow the dynamics of what's going on later. Okay. Now, if we want to look what it does, or where is our this Northern Red Sea part on the terms of nutrients for the global ocean, so it is right here. So it is really very low, and it should be low, and this is what is called an oligotrophic sea. And that's how it should stay, because if we look again at this, and we look what is going around the shores of all this Gulf, as well as in the Red Sea, the whole Red Sea are circled by those beautiful, lush, fringing reefs, like that. And what they are really like oases in a desert, because they are really adapted to have such high productivity system in a very oligotrophic sea, and that's how it should operate. And that's how I want to show you here. If you look at this reef, this is the Nature Reserve Reef. And if we look at the reef and make a cross-section through the reef here, and what you see, if you look at the chlorophyll, you see that, you see that the chlorophyll goes down as the water flow from the open sea through the reef. Markedly down. That's a big change. phytoplankton is being reduced. If you look at the zooplankton, while it flows over the reef, you see that it also reduced the concentration of zooplankton. And if you look at the nutrients, and this is, let's say, nitrite or phosphorus, and if you look through the reef what's going on, you see that it goes vice versa. The phosphate or the nitrate here, the nutrients in the reef are higher than in the open sea. This is the open sea. This is, by the way, depth in meters. This is in 100 meters, so this is 200 meters from the sea, and this is 20 meters depth. And what you see that the highest concentration is in the reef, and it's like you have a gradient from inside outside. So if you sum up with the modeling and everything, which I will not elaborate here, but to sum up in a picture, it looks like that. You have a reef, you have a flux of phytoplankton and zooplankton here, and the reef is like a food processor. It takes this and emits out nutrients. So this is really a grinding machine, and it operates in an oligotrophic sea. Otherwise, if you have, so that's why, how it works nicely when the nutrients, when the mixing is shallow, and the concentration of nitrate, it's surface water where the reef grows. It is not growing down here. It is growing only in the surface at a few tens of meters. When it is like that, it operates the way that I showed you. But when the mixing is deep and the concentration of nutrients is high, what happens is something like that. If you see here, the reef starts to grow a beard. This is a beard of macroalgae. And they cope with the reef. They really compete with the corals, and they grow on top of it. So this is actually a potential threat to a reef, high nutrients at surface water. And how you can get it, such a threat is by combination of high nutrients in deep water. Why? Because in a deep mixing event, they can jack up to the surface and then trigger what is called the eutrophication event and a macroalgae growth. Actually, something like that happened in 1992, and we had the chance to write a paper in Nature about it, which shows this. You see a green reef because it is covered with algae. And actually, during that event, only 20% mortality was in the reef of corals. That's what indicated by the biologists. Okay, so let's see now what we see over time. If we know roughly the basics, how it operates, so we can go ahead and look, let's say, dissolved oxygen as an example and nitrate. Now, they are interconnected, and again, I apologize if everyone knows it. I apologize, but maybe not everyone, so I give a small a basic, which is in photosynthesis. You take CO2 and nutrients and water, and you make plankton and oxygen, while in deep water, respiration does vice versa. You take dead plankton, if you want, oxygen, and make CO2 and nutrients and water again. And the ratio, something what is called the Redfield ratio, is something like that. It is about 138 moles of oxygen per 16 moles of nitrogen and nitrate. Now what we see here again, if we plot the concentration of oxygen with depth over time here, from the 70s down to this year actually. And what you look, if you go to a certain depth, which was also in the 70s and also now, because deep water were not encountered in the 70s while they were sampling then. But what you see is that if you look at the colors only, with time you see a decrease in oxygen in deep water. Even that you see that you have replenishment here, high and here, because of, again, deep mixing event. Deep mixing event replenishes the oxygen of deep water, but the game starts again. The difference was about 10 micromolars per liter. And you see it here, even if we zoom in into the oxygen in deep water, let's say from the year 2002, 3, 4, you see a gradual decrease of oxygen in deep water, even that you see some of the mixing events, you see them, but not complex mixing, but it goes and keep on decreasing. Now if you look at this decrease, and you calculate how much you have to see an increase in nitrogen, you have to see that amount of increase in nitrogen. And actually, if I zoom only to the picture that we saw before, but now between 99 and this year, and what you see that the decrease in oxygen that you see here is really accompanied by an increase in nitrogen. You see that the colors of nitrogen are warmer and warmer, which are higher. And again, the mixing events reset the system, but even that there was a reset in the system, the concentration keep on going up. So what we can see that on long term of this decade, oxygen decreased and nitrate increased. Now let's see what was the inventory itself, because it tells even a nicer story. And the inventory is only the oxygen concentration, the oxygen content over 1 meter square of seawater, the whole sum up of the oxygen. And what you see that since the 70s, it did something like that. It didn't change almost. We don't have data here. It decreased, and then it decreased between those two mixing again, even higher. This decrease is something like 1 mole per meter square per year, and the decrease after this mixing was even faster. 3 times faster. And then this mixing. So what happened here, this may be this perturbation that I want to talk about. So if we now zoom a bit more, and we see here this, I don't know if you can see those 3, but you can see it even in Google. These are those fish farming in the northern part of Eilat. These fish farms. And this shows or summarize what we know now, what was the emission, nitrogen and phosphorus emission from those farms by calculating what they feed to the fish. And most of what is fed in is really emitted to the environment, and only a small part of it is really caught as a fish. So this is the emission. And this emission, if you look at it yearly, it went up quite a lot since the 90s. Then it dropped a little bit, and it stays constant as far as I know. It is about 2 to 5% of the total nitrogen input inside, which may be not big. But if you look here, and we'll see later, if you look here in the northern part, it is amount to 50% of what we call the new production in that part. So that's a huge number. Now, if we go to the dissolved oxygen, and we put on the same perspective the time of the fish farming, you see that when this goes down here, this went up. And if I put it on this picture of the inventory, you see that it decreased here and stays, and after mixing, this stayed still high. That's the total emission at the time. It stayed high, and this decreased even more, the oxygen. Decrease of oxygen, it means input of organic matter. Why? Because you input nutrients. You make extra phytoplankton, which is going down and consuming oxygen. Now the deep mixing, 2 deep mixing were 2007, 2008, and we don't know what's going on later, and we will have to see. Now, what's going on with this thing that this picture that you saw was pretty alarming, and the scientific community came with an outcry, and it went to the government. And what they did, they decided, finally, after having a committee and debate and argues for several years, which one of the professors from this university, Yossi Loya, was really a very materializing this thing, they decided to dismantle it gradually. So if this, how it looked, let's say this part, the three cages that we saw from the Google, this is another system. But this is how it looked in 2006, and 2007, one of them was already out. But it's still not completely out. So what I think that, let's say, maybe it dropped now to this level, but it still didn't drop completely. Okay. So if we do this calculation, as we said, it is 2 to 5% of the total emission from the Strait of Tiran, but it amounts to what we called is about 50% of the new production. So all the new nutrients that come every year to support phytoplankton productivity, 50% of it came up from this fish farm emission. So it's not small at all. This is what we call this eutrophication. By the way, people were talking about global warming, and so by this time we measure temperature, we measure various other things. So I saw that people were talking about it. So you see here the temperature from 88 to 2006. This is surface water, deep water. You see that there is an increase. But if we zoom in down here is only from 88 to 2006 and only deep water. I don't know if you can see it, maybe. But look at the deep water. Deep water can change only during mixing, because you mix the water column, part of the water, and you inject heat down. And look at that. There is deep water have really a 0.35 degrees C in 10 years increase, which maybe says something about this Gulf as a thermometer for global warming. It's small enough to exchange heat fast, but it is big enough that it will not change. The temperature will not change at all. So maybe it's a nice sensor, if you want, to see how the temperature changes. But it really changed. So maybe it is true, maybe it is not, I don't know, but it's only worthwhile to mention. Anyway, we have other corroborating evidence for eutrophication. If you look at the primary productivity, which was measured in this Gulf over the years, so you see that from the end of the 80s till the end of the 90s, it was here in that level. Even in the 70s, there is one measurement that was still the same. But since 2000, it went up a lot. High productivity is eutrophication. If you look here at the reef, which we measured the growth rate of the reef framework, it is here. It did something like that over time, since 90 to 05. And a decrease in reef growth, it means higher nutrient input. You see it nicely if you compare the year 2001, 2004, August or September of October in reef growth, you see that it dropped from year to year. Now, if you take data from Yossi Loya, from Tel Aviv University, on the cover of coral colonies, with time, you see a drop. But if I plot this a little bit different, like a geochemist would do, over time, and that looks even more alarming than it looks in the other picture, you see that the cover of corals on the reef over time went down. And it looks like that. Again, from publication of Yossi Loya, that the amount of live colonies dropped markedly. Okay, so what can we say now? As to sum up, it was at least the eutrophication phase. Did it end because or will it end due to dismantling and deep mixings? I don't know. That's it. Thank you.
I wish to thank all the speakers and the Dan David laureates for bringing us this exciting the information that for me it was very exciting to hear and to learn a lot. Thank you very much. We don't have time for the panel, unfortunately. And I want to close the day. Thank you again. Bye. Shalom, shalom. Is this yours? Just to remember, it's that, you remember? 456. 456. It was nice to meet you. And, tomorrow you will come to visit us. Yeah. Me too. Yeah, we'll send a taxi, so maybe 8, 15. I'll give you a call, so I'll ask the driver how bad traffic is going to be.
Sure. That sounds good. Very good.
Taxi drivers.
Yes, they
Okay, so I'll call you. Maybe leave a message.
or leave a message.